Well, here we are again. This is just a quick update on my progress with the IC tester. As you can see up here, I've actually renamed it now to the MegaIC Tester because it's got a lot more functionality than the original one did, and it's obviously based on the Arduino Mega. Just to give you a quick overview, I've updated the case. It's now got a holster for the stylus, which we can just pop out. Right, I'll use it to drive the screen, and then it just pops back in again. On the back, I'll put my name and the name of the tester. So, right, let's have a look and see what I've been up to with this thing. Okay, so what have I been changing? Well, apart from the new case, which by the way is available in both left. There's the slot there for the thing on the left, so for left-handed and right-handed people. I've made some serious performance improvements. There's a new immediate mode, and it's much better in terms of how it shows you good and failing elements on chips. I've improved how clocks are handled. I've added support for bi-directional pins, and some other stuff. So we'll just start at the top and start working on it. Okay, so one thing you might notice is we've got a re-index function on here. I've added an index file for the database, so now if there's a lookup required, it goes and looks in the index, determines whereabouts in the database the chip it wants to work with is, and just goes almost directly to it. So if we, this is a 74165 chip, so if we do a test on the 74165, it immediately found it and it's testing it, and it says it's good. So that shows you how fast it is. And if we go back to the main menu and we look at the index, well, the way it works is if the tester determines that the database has changed since the last time it was used, it then goes and runs an automatic re-index, or we can do it manually. So we'll do it manually in this case. So it's indexed 186 ICs, and 96 of those have pinout information. I'm still working my way through adding the pinout information to all the chips and adding some more chips as well along the way. So it's now that it's re-indexed, I can still do identify. So not only have we got support for 14, 16, 18, 20 and 24 pin chips, we've also now got an all option. So this chip behaves like a 4053. It's running through all the chips in the database. So there we are. It's actually a 74165. So what I'm going to do now is I'm going to take the 74165 out. I'm then going to put a 7400 pin 7400 IC in. So we'll test the 7400. There we go. All four elements are in good condition. We'll look at the pin out and run through the four test cases. There you go. They're all done. Okay, so that's a chip that's in good condition. Pop that out, and now if we look, we've got here a 7402, which, oh dear me, one of its legs seems to have fallen off. Oh look, one of those is also bent. So we'll pop this one in and see how the tester copes with that. So we'll test it. 7402 says it's bad. Now the element status is shown in amber because we've got four elements on this chip. Element 1 is bad, elements 2, 3 and 4 are good. So if we go into the pinout view, right, again we've got the various elements displayed, each one colour coded, yellow for the first, purple for the second, green for the third and blue for the fourth, or cyan. And you can see here that the all of the controls, inputs and outputs for a failing element are highlighted in red. So if we actually step through, so this is the first test case of 4, and that's fine. Second case fails because this output here would be expected to be low and it's high. Same again, same again. So this allows us to see which element of the chip is failing, and we can then concentrate on that to try to understand what the problem with the chip is. Now, if I pop that out and pop the 7400 back in again, I can show you what happens when all the elements on a chip fail. So this is a 7400. What I'm going to do is I'm going to do a test, but I'm going to tell the tester that it's a 7402. Now it's showing us that all elements stayed at all of the state. It's now showing us that the status of all elements is red, so therefore the whole chip is deemed to be bad. And if we look at it, all of the inputs, outputs and controls for every element are highlighted with red squares on the chip itself. If I do a test on the 7400, it's a 2-input NAND gate. So we would expect the output to be low if both inputs are high, and under any other circumstance we would expect the output to be high. So here you go, both our inputs are low and the output is high, and we had our manual test mode where we didn't show any of the outputs. We could then manipulate the inputs, hit the test button, it applied the inputs and controls to the chip and then showed us the outputs. So on this element we've got both inputs high, and as it's an AND gate that would mean that the output would go high, but because it's an AND gate that means the output goes low. So this is working fine. However, if we want to be a bit more interactive, I've now done a new immediate mode which we switch to just by clicking there, and now instead of hiding all the outputs it leaves them all on display. And we can now manually interact with the inputs and controls, and those changes are immediately applied to the chip. So there we go, the output's gone high again, it's gone low, it's gone high, it's gone low, turn them both off, it's still high, and we can do that with any input or control on the chip. Now, you wouldn't normally do this if you were working with something that, say, was using a clock, or where you had to change multiple inputs and controls before applying them to the chip. But for things like simple gates, it's an interactive way of testing the chip. It's very quick. Something else I've done is I've enhanced the clock handling capability of the IC tester. The original version could only cope with a single clock input on a chip, whereas I've enhanced it now so it can cope with as many as are needed. What I've done is I've put a 74393 in the slot there at the moment, so if we go and test that, says it's good. It's a dual 4-bit asynchronous binary counter with reset. Both elements are good. Go and look at it. Okay, so there are 15 test cases here, and if we actually follow through the test cases, you'll see that the clock on each of the elements is risen and then lowered and then risen and then lowered. That's because this was the original set of test cases that came with the original IC tester. And you'll also note that the clock signal is active low, so it will clock on the falling edge, not as a lot of clock signals do on a rising edge. Now I've enhanced the tester so that, as well as having the low on this clock pin and a pulse, you can now have a negative going pulse and a high. So low, positive going pulse, negative going pulse and high. So that allows us to easily test something like this. So if we go, if we actually init the test case, go through, it's now starting, the clocks have both gone high, and as they go low, there we go, went low, output 1 on each of the counters goes high, So we're now counting up in binary on the outputs on each low going clock signal. Now if we actually flip this into manual mode and we change that to a negative going pulse and we hit test, then what we've got here is we've got a negative going pulse being applied to the clock for element 1. The clock for element 2 is low all the time, and we can now keep on hitting the test button and it'll keep on applying a negative going pulse to the clock signal every time we press the test signal. So there we go, we've got element 1's counter counting up, and element 2's counter is not moving at all. Put the 74165 back into the ZIF socket to show you a new facility I've added whereby you can add comments into the database file for the test cases for an IC, and as you're running through those test cases it will display those comments. So there we go. So this is a 74165, it's an 8-bit parallel in serial out shift register. So it's got 8-bit positions. We have the capability using the shift stroke load line to force values into the shift register. So we've got inputs A, B, C, D, E, F, G and H, and if the shift stroke load line is low, then we are loading whatever's on the inputs into the shift register. If the shift stroke load line is high, then we're in shift mode, and the bits will shift up the shift register whenever there is a clock signal and the clock is not inhibited. So what this says here is load all zeros and expect a low Q. So we're in load mode because the shift stroke load line is low and we've got no clock, the clock inhibit is not enabled, and therefore we are loading all lows into the shift register. Now this shift register, the outputs reflect the state of the H bit, and we've loaded 0 and we're still loading 0 into the H bit, therefore output Q is low and the complementary output not Q, is high. So what's the next step? We're going to put a high into the F bit. We're still loading rather than shifting, and because we haven't put a high into H, output Q is low still, and output not Q is high. What's the next step? We're going to put a high into the F, H and B registers, and we're going to expect high on Q because, as I said, whatever's on the H bit of the shift register is reflected on the outputs. So because we're putting an H into, we're going to put a high into the H bit, output Q is now high and not Q is low. So what we're going to do next, we're going to start the clock. So we've moved the shift stroke load line into shift mode, we've applied a clock, and now what we're going to be doing is those bits that we loaded in to the shift register on F, H and B, we're now going to shift those up the shift register every time we do a clock pulse. So this says we're going to expect a low, which we've got on Q, followed by a high, followed by a low. So there's the high, there's the low. Okay. Next step says it's going to send in a high on the serial input, and because this 8-bit parallel to serial shift register can be cascaded, whatever comes in on the serial line when there's a clock pulse gets fed into the A bit of the shift register. So because we've still got those bits that were on F, H and B which are being shifted up the shift register, we're now adding something into the A bit as well. So what this says is we're going to expect a low, low, high, low, 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 high, low on Q. So low, low, high, low, 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 high. That's the one that we set in from the serial input earlier on, and then we're back to low. So that's a full set of test cases, and that shows the way that the comments that held against the test case are shown on the screen. Just to make sure that I can do some proper testing on the chip tester, because I didn't have that much in terms of ICs to evaluate it with, I went and purchased this, which is a whole bunch of 74HC ICs, and I also purchased this, which is a whole bunch of 4000 series CMOS chips. So I'm gradually running through, making sure that all of these behave as they should using the tester, and that's highlighted a few issues which I've now resolved. And there are various chips in these collections which I don't have in the database, so I'm adding those through as I go along. Another enhancement I've made to the IC tester is better support for bi-directional pins. The original tester did support bi-directional pins because you could set any pin to be forced high, forced low, expected high or expected low, but obviously in interactive mode that's not a lot of good. So what I've done is, if we put this is a 74243 chip, so it's a 4-bit tri-state non-inverting bus transceiver, and the key bit there is transceiver obviously. It's got 2 elements on it, yep, 4-bit, 2 of those go into the pin out, and these pins, instead of pointing inwards or outwards, are diamonds, and they show that they can point both, that these pins can function in both input and output modes. So the names of them are, oops, I'm going to have to fix that, input and output 1, 2, 3 and 4 on the yellow element, and ditto on the magenta element. So if we actually look at the test cases, we've got data coming in from the purple side or magenta side and going out of the yellow side. So all those zeros there are now reflected on here. It's now flipped around the other way, so the data is coming in on the yellow side and going out on the magenta side. And so we've got highs on here, highs on all the outputs, and the final test case is lows on the inputs and lows on the outputs. Now if we flip this into manual mode, because these pins are outputs, they all go and they all get hidden. So now on the pins that are bidirectional, you can now set that as high, or you can set it as an output, that's showing as an output because it's disappeared, or you can set it as low or high or an output again. So if we flip all these back to outputs, we can then flip all these back to inputs, flip this one high and flip this one high, change those 2 pins there, and then this side should be outputs and this side should be inputs. So when we hit the test button, we get the inputs reflected on the outputs. Now it's a bit clunky, and I actually intend to make it so that the change of type for bidirectional pins is done within the chip, and the things that are in the modes that are available on the pin are only appropriate to the mode that the pin is in, but that'll be for the next release. So that's how we deal with bidirectional pins. And yes, I've got to fix this. I've obviously put too many characters in the pin name there. It only supports 9 characters, and I've obviously put 10 in. Plonker. So if you're curious as to what the IC tester looks like on the inside, I've taken the top off, which is just part of the 3D printed case. We've got the 2.4 inch 320 by 240 LCD, sorry, TFT board here. We've got my custom made, fairly crude ZIF socket board, and if I just pull this out, okay, so there it is. It's rather strangely wired, but that's in 3 dimensions. But that's only because on the Arduino Mega there are restricted places where you can actually run cables through on a board that's hardwired like this. So that's why the 3D wiring has been done. I'll just pop this board off, and then you can see the Mega underneath. So there's the ZIF socket, there's the Mega in the case. I've put captive nuts in the bottom of the case, so the Arduino is nice and secure. And there's the LCD board, which also has an SD socket on it, which is what is used to hold the database file. Don't know if you could see my finger there, but there's the SD socket there. So there it is with all its clothes off. So that's a summary of the updates I've made so far. And just to look at the current project stats, the database has now grown to 186 chips, 96 of which have got pinouts. The source code is now at about 3,000 lines, about 88k. The current memory usage in the Mega is 74k out of 253k, and the RAM usage is 4,243 bytes out of a possible 8k, but that doesn't include local variables. I'm going to be moving some of the chip data that's currently held in arrays into the flash memory and accessing it from there. So that's something else that I'm working on to get myself more RAM, because I've run into some problems recently where I've run out of RAM. So in terms of what happens next, as I mentioned earlier, I'm going to improve bidirectional pin handling. I'm going to add the facility against a test case whereby you can tell the chip tester that it needs to apply the controls and inputs to the chip multiple times, and then only check against required outputs at the end. So this will be used for testing things like counters and dividers, in as much as you might set up the counter initially with 0 in it, then run 512 tests, 512 counts, and then check that the output at the end is indeed 512 counts. The other thing I want to do is add a graphical display of the chip elements. So it will actually show you hands, NORs, NANs, XORs, those sorts of things. And finally, I'm going to add attributes to the database for the chips. So if you want complementary inputs or Schmidt trigger inputs or open collector outputs, those sorts of things, you'll be able to search the chip database and it will show you what is available in the tester that supports those capabilities. That's a bit of a, it might not be required to do that one because the internet's out there, and if we want to do chip searches, that's probably the way to do it. So that's a fairly low priority thing. So if anybody's got any other suggestions, I'd be more than open to taking them and seeing where I stick them in the development schedule for the MegaIC Tester. I hope you enjoyed this video, and I'll leave you there. Thank you. Bye.